right? This is going to be the last little segment for the first two sections of our chapter 14, which introduce the concepts of the iterated integral, and in the case of these sections, the double integral. There's a lot more to learn about double integrals, but the basics of the region of integration, the limits or boundaries that go with those regions, and the order of integration, and then the function itself, which is our dimension number 3. Remember, we think of that as our, z equals some function of x and y. All of those pieces work together, and we need lots more practice. But let me just show you this one more example. We're actually going to try to integrate this particular problem, and we haven't done that for a few segments. So as a recollection, if you want to integrate e to the u with respect to u, that's one of the nicest functions ever. But the key is that you have to have those two pieces working together with you. In our particular problem, u would be equal to negative y squared. Now, if we took the derivative with respect to y, we'd have negative 2y, and that leads us to our differential. Du is negative 2y dy. But this factor of y doesn't exist here. We don't have that at all. So we're not going to be able to integrate this in its current form. I'm just going to put a no factorial here. So here is our only strategy we have right now on our list, and that is to possibly switch the order. Could we create this integral as dx dy? So to do that, we're going to look at the region first. Hear that? There's my frog serenade again. It's fantastic. So the region of integration for this particular problem, the constants in the last integration are of the variable x. So x goes from 0 to 1. So again, if you've been paying attention, I've been thinking of that as from left to right. X goes from 0 to x goes to 1. And then if we think of it from bottom to top, according to this, y equals x is the bottom, and y equals 1 is the top. And if I were to draw that out, here's y equals x, and here is y equals 1, a horizontal line. We're looking at this region. That is the region of integration. So we're going to switch the order of integration, and that is now our go-to picture. So we need the picture. We don't need everything else right now. What I am attempting to do is to set up this integral, e to the negative y squared, but have this be in the order dx dy. So these would be y equals, and they should be constants. These would be x equals. They can be variable. I'm still going to be looking at this from bottom to top and from left to right. Again, that's not exactly the way the book writes it, but it is what the book means when they say that. So if we look at our region here, the y values go from y equals 0 to y equals 1, and those are going to be constants. So it's from 0 to 1, y equals 0 to y equals 1. And as king of all partial credit seekers, I'm just going to go ahead and write that in. So I could say, hey, look, I've got some of the correct answer here. Partial credit, right? Left to right. Let's do it the style I've been doing it here. I want to write them as x equals equations, but I'll start with a description. the left boundary is the y-axis, and the right boundary appears to be this line. The line keeps changing its location. These rectangles are getting longer, so there must be a variable there. So I'm going to put a little note here. Y-axis is on the left, and our other line is on the right, and I need to write these equations in the form x equals. So like I said, this is like a description. Now we need the actual DNA code. Well, the y-axis is also known as x equals 0. And that line, y equals x, can also be written as x equals y. And I'm just going to fill in those blanks here. X goes then from 0 to y. And now we're going to try to determine if we can evaluate this. So let's see. All right. X is the variable. That makes this a very unusual looking constant. When we integrate, again, there are sort of imaginary or undrawn parentheses or brackets. The integral of dx is just going to be x. We're basically just being asked to integrate this. That is nothing but a constant that will factor out of the integral. So this will become, from 0 to 1, dy still remains, x times the constant e to the negative y squared, and the x boundaries go from 0 to x equals y. And by the fundamental theorem of calculus, if x equals y, I'll substitute it in here, e to the negative y squared, and if x equals 0, I'm going to get 0. So now we basically just have to integrate this expression. Now, have I made any gains? Did I just delay the inevitable, we're stuck forever? Or can I integrate it with just basic techniques or more interesting techniques? We always will try u substitution first. So let's try it out here. If u is negative y squared, du is negative 2y dy. And my students, now I have that factor of y. I have a dy here. Y times dy is du over negative 2. When I rewrite this integral, I'm going to now do something I sometimes show my earlier semester calculus students. I don't want to pause what I'm doing. I can either change these boundaries to match the new variable, or I could just do a temporary placeholder. So I'm going to put an arrow here because what I'm about to write is not truly equal. I'm using this sort of as finding a legal way to put my work in the middle, but maintain the problem here if I need it. All right, so let's do this. We'll just worry about the boundaries after I come back. I'm going to have e to the u du over negative 2. This is going to become negative 1/2 e to the u power. Now one more conversion. U was equal to negative y squared. And according to this problem, my y equals boundaries were from 0 to 1. If I want to evaluate this, negative 1/2, y is 1, I'm going to get 1 squared is 1, e to the negative 1, and minus e to the 0. E to the 0 is positive 1. This is 1 over e. If I distribute the minus sign, I will get 1/2 minus 1 over 2e. Or you could leave the 1/2 factored out. 1/2 is bigger than this, so you should get a positive value of something that might be considered volume in this case. Now, last but not least, let me just point out in our textbook there are a number of problems in the first 2 sections of the chapter that are similar to this, where you have to sketch the region, switch the order, and I cannot stress enough, practice, practice, practice. Integration, but also the regions of integration and switching the order. I'll be providing some more practice problems as we go through the chapter, but you're going to have to take advantage of what you can. All of the odd numbers have solutions in multiple places that we've talked about before, so go for it. Good luck.